rather than just discussing reaction rate qualitatively, I do want to talk about it quantitatively as well. And so what we're going to be looking at in this video are a couple of the real consequences of substitution. Some of the things you have to think about whenever you're doing electrophilic aromatic substitution on substituted benzene rings. So we're first going to look at the rate of nitration of benzene relative to substituted benzene. And we're going to specifically look at relative rate constants. Okay, so here's the reaction scheme that we're going to be following. So this is a nitration reaction. You can see we're starting with an R group on the benzene ring, and then the nitration reaction is going to put some nitro group around the benzene ring. Okay, and so in drawing it like this, again, when we draw it kind of off to the side or through a bond, we're saying that nitration is occurring, but we're not specifying necessarily where that nitration will occur around the ring. But we can use this just to look at relative reaction rate. Okay, and so if we start off with benzene, where R is just hydrogen, right, we can say that the relative rate constant, which we'll refer to as K-rel, is going to be 1. All right, so we're not saying that this is the absolute rate constant for the electrophilic nitration of benzene, right? Well, all we're doing is we want to compare how substitution is going to affect the reaction rate relative to benzene. So we're just arbitrarily setting benzene at 1. K-rel is, again, the rate constant for the reaction. So if we have a higher number, a higher K-rel, all that means is that the reaction rate is going to be increased. If we have a lower K-rel, a K-rel between 0 and 1, that just means it's a slower reaction, or the reaction rate will be decreased. All right, so if we look at the consequences of just methyl substitution, right? So if we change that hydrogen to a methyl group, right? Think about what that is going to do to the reaction, right? So we learned in the previous video that a methyl group is an electron donating group. Remember, and donating groups are going to be activating and therefore speed up the reaction. So in this case, we would expect the K-rel to be greater, and in fact, it is. So relative to the nitration of benzene, the nitration of toluene is going to be 25 times as fast. So the rate is increased 25 times by putting a methyl group onto that position, right? So it's already just a methyl group is already much faster than benzene itself. If we change that to an even stronger electron donating group, right, something that has a pair of electrons and can actually donate those electrons into the ring, so anisole, so when we put a methoxy group on that benzene ring, the relative rate constant jumps up to 10 to the 4th, right? So 10,000 times faster than just regular benzene. All right, so these are both electron donating groups. All right, and electron donating groups, as we learned in the previous video, should speed up those reactions, and in fact we see that those rate constants relative to benzene are much greater. All right, now if we look at electron withdrawing groups, all right, let's start out with a carbonyl. So how about an ethyl ester? All right, now this is an electron withdrawing group, so the uranium ion that's formed whenever this undergoes substitution should be destabilized, right? Should be higher in energy relative to benzene. And so these reactions should occur more slowly than benzene. And so in fact, the relative rate constant for this ethyl ester is going to be 0.0037. All right, and so just for some reference, what that means is that this is going to be 270 times slower than just regular benzene. The substitution of ethyl benzoate is 270 times slower than benzene. All right, if we look at some other electron withdrawing groups, right? So this is a resonance electron withdrawing group. Now let's look at the effect of an inductive electron withdrawing group. So trifluoromethyl, right? The fluorines are pulling electron density away from carbon, which is therefore pulling electron density away from the ring, right? The relative rate constant for nitration of trifluoromethylbenzene is going to be 2.5 times 10 to the negative fifth. Right, so I calculated this before I started the lecture, and that's going to be about 40,000 times slower than the rate, substitution rate or nitration rate of benzene. Okay, if we look at two more electron withdrawing groups. So we're doing nitration. Right? What if we put a nitro group, or what if we start with nitrobenzene and try to do a subsequent nitration of that molecule? Well, that's going to be really pretty difficult, right? The relative rate of the reaction, 6 times 10 to the negative eighth, right? And so in terms of how much slower that is than benzene, it's 16.7 million times slower than benzene, right? So doing electrophilic aromatic substitutions on nitroarenes, nitrobenzenes, is actually fairly difficult to do, right? Your reaction conditions need to be pretty extreme, and the molecules that you're using need to be pretty resistant to those extreme conditions in terms of their degradability, right? So we want the molecules to react, not break apart. So you often don't see electrophilic aromatic substitution occurring on really, really electron poor benzenes. Okay, finally, let's look at an interesting electron withdrawing group in these trialkyl ammoniums. So we'll say our aryl trimethyl ammonium. All right, so this is an amine that has an extra methyl group on it. So it's positively charged, which means that the carbon-nitrogen bond is very, very strongly polarized toward nitrogen. Okay, so this is a really electron-poor aromatic system. That's illustrated by its relative reaction rate constant of 1.2 times 10 to the negative eighth. Right, and what that works out to is about 83.3 million times slower than benzene. Right, so these really strong electron withdrawing groups are going to significantly slow down those electrophilic aromatic substitution reactions. Okay, now it's as you might have noticed, one thing that I've avoided talking about so far is halogen substitution. Right, so we have our halide series where we can have a fluorine, chlorine, bromine, and iodine, right? And the one thing that we have to realize is that these bonds, some of them anyway, are going to be polarized somewhat strongly in some cases towards the halogen, right? So the halogens can pull electron density away from these benzene rings, right? The other thing we have to consider is that each of these halogen atoms is going to have 3 non-bonding pairs of electrons. Okay, and so there's potential for those electrons to be donated into the ring through resonance. And so it's not super clear whether these are going to be electron donating or electron withdrawing. But if we consider the reaction rates, or the relative rate constants for each of these relative to benzene, right? What we see is they're actually a little less reactive than benzene. So all of these halides, in terms of reaction rate, are going to behave as mildly electron withdrawing groups, right? So in the case of fluorine, the relative reaction rate is 0.15, right? In the case of chlorine, 0.033, bromine 0.030, and iodine 0.18. Right, so this is kind of an interesting trend where the fluoride, the aryl fluoride and the aryl iodide are going to be the most reactive of these four. All right, all of them are less reactive than benzene, but of these four, the aromatic fluoride and the aromatic iodide are going to be the most reactive. And then the chloride and the bromide are going to be the least reactive. All right, and that's something that we'll investigate later on, but it's good to kind of put them in the context of all of these other electron donating groups. Electron withdrawing groups, all right, and then we'll qualify these kind of separately as halides. All right, and you'll see later on why we're putting these halides into a different box, even though they do have some electron withdrawing capability. Okay, the other consequence, the other thing that we have to think about whenever we're doing electrophilic aromatic substitution is how the substitution is going to affect the reactivity of a product. Okay, so we know if we take benzene and we treat benzene with nitric acid and sulfuric acid, we are going to make nitrobenzene. Right? One thing that we do not have to worry about in this case is a subsequent reaction occurring where we're putting two nitro groups on that benzene ring. Right? Because as we just learned, a nitrobenzene is going to be much, much, much less reactive than just benzene. All right, so when we're doing this reaction and we have the benzene and our product all swimming around in that reaction soup, right, we can be pretty confident that any nitration reaction that occurs is going to occur on benzene and not on the product, right? Because our product in this case is less reactive. All right, and our starting material is more reactive, right? Electron poor benzene and just an electron neutral benzene. Okay, but if we're doing other reactions, say we want to do alkylation, so we'll take benzene, we'll do just add a tert butyl group, so we'll take T-butyl chloride and catalytic aluminum chloride. And we add that tert butyl group on there. All right, so what we did was we just added an electron donating group to a benzene ring. And so we are now in the situation where the product that we're making is more reactive than the starting material, which is less reactive. The consequence of that is that because whenever we do these reactions, the product and the starting material and all the reagents are going to be swimming around in that reaction soup at some point, the likelihood of us doing another substitution on the tert butylbenzene is more likely than doing substitution on benzene. And so what we'll see is that it's really difficult to stop alkylation once we add one alkyl group, right? Because the product we're making is going to be more reactive towards substitution than the starting material, right? If we want to think about these reactions, right, this reaction, second reaction, should be faster, and the first reaction should be slower, right? Just relative to one another. Second reaction will be faster than the first reaction. First reaction will be slower than the second reaction, right? So it's really important to think about the consequences of these substitutions, how they're going to affect the reactivity of the benzene ring, right? And whether or not it's likely that the products will undergo further substitution reactions.